So why Gaussian process? So Gaussian process, it's kind of very commonly used in scientific field because, you know, you like, because not only you can put input time, you can input other things, you can input model parameter. So Gaussian process can become an emulator for you. So it's kind of, it's a nice paper by Tenzin Edwards. It's kind of using Gaussian process to emulate what's the global sea level response to different ice sheet melting parameters. And you know, the second it's in a kind of also famous paper by Robert DeCanto is also using Gaussian process, where your input is actually modeling parameter instead of time. So you can kind of interpolate between different parameters, and you can use those interpolation for predict future sea level. And lastly, like the spatial temporal sea level modeling is kind of really powerful as well. If you know this kind of IPCC AR6 and NASA sea level projection tool for vertical lab motion, it's actually a spatial temporal Gaussian process. So it's kind of, you input the spatial temporal Gaussian process and you use those information to predict sea level of vertical lab motion in the future. So this is really a powerful tool. So I was really excited to introduce them to you. So hopefully you can use that in your future research as well. So next thing we want to talk about is kernel, right? We mentioned that we are modeling, so we, based on the square distance function, we need to model the covariance, right? The different choices of covariance function or different choices of kernels have a direct impact of your prediction. So here you can see some different things about the covariance function. Here is a square exponential covariance function we used before, right? It's here. So you can see if we can draw some samples for using these kernel choices. It's kind of as we saw before, right? And but we can use some periodic kernel. So in that case, the prediction is kind of periodic, and we can also use linear kernel. So the prediction is a linear, is similar to linear. Question? Or okay. Okay, no. Okay. So it's kind of like, it's really like the kernel choices, it kind of really kind of reflect your prior knowledge of the process you are interested in, and different kernels have different properties. So if you think about here, even if you have same amount of data, depends on what kind of kernel you are using, the inference, the posterior inference is really different, right? So here I want to highlight the first thing about kernel. It's like how much differentiable of each kernel. So we are using RBF kernel. It's kind of, it generates some curve that was really smooth. It's kind of indefinitely differentiable, which means the process is changing really smooth in time and space. What that means is that you cannot have abrupt change. So here, as an example, here you can see that the black dot, if we think about that was our observations, if you are using the RBF kernel, this RBF kernel can only generate prediction that was changed gradually. And you see that this gradual change definitely doesn't fit well with these observations, right? So this kind of RBF kernel is not, it's not suitable for many applications in sea level, because we know we can have abrupt sea level change, not only in time, but also in space, right? If you're moving from the land to the ocean, you have abrupt change. If you're moving from some estuary location to some terrestrial location, you have different different sea level change. So this can be changed quite abruptly. So the RBF kernel you see here, some sample here, it's not that suitable for many applications in sea level. But if you have some computational experiments, for example, you kind of, if you're changing the physical parameter, you kind of expect the prediction is changing smoothly according to your physical parameters. So sometimes this RBF kernel is quite suitable for do some computational emulation, those kind of things. But here we are introducing something called maternal kernel. So maternal kernel is like allows you to define different level of differentiality. So here we are using the 3-2 maternal kernel, which is once differentiable. So if you see if you see this kind of curve, it's kind of less smooth than the RBF kernel. So if you see the prediction by the maternal kernel as this a green line here, which is kind of changing, it can change more abruptly compared to this red line, which is, changing really, really smoothly. Okay, so let's try it to use different kernel in our PaleoSTEHM. So here, okay, okay, so here we are using an RBF kernel, right? So as I said before, here we are modeling the New Jersey sea level data as we saw before. Here is we are using New Jersey sea level data, and we are using an RBF kernel to model the New Jersey sea level data. So as you should see before, the model definition is quite similar, but now we are inputting the y sigma from geological reconstruction into this Gaussian process model. Okay, so in this way, the model level is known. It's from the geological reconstruction, and we are trying to optimize this model. It's pretty much the same, right? And we can make some prediction based on the RBF kernel, right? You see that the sea level is changing really smoothly, and the rate is really changing really, really smoothly. So maybe you cannot feel how smooth is that. So let's use a 3-2 maternal kernel here. So here, to use 3-2 maternal kernel is really simple in PaleoSTEHM. So instead of define kernel as RBF, you define kernel as 3-2 maternal kernel, right? You see here and here. You're just changing the kernel choices in here, and you do exactly the same thing, and you can make prediction based on 3-2 maternal kernel. So there are a list of available kernels in PaleoSTEHM. In the PDF, I sent that to you, so you can check it out later. So if we're using 3-2 maternal kernel, you see that, okay, the difference, you can clearly see have some more temporal pattern because the differentiality is much lower compared to RBF kernel. So it's kind of can change more, the resulting curve can be changed more roughly compared to RBF. Okay, and the maternal kernel family, so they have a lot of maternal kernel. We have 3-2 maternal kernel, which is once differentiable. We have 2-1 maternal kernel that was non-differentiable, and we have 5-3 maternal kernel that was twice differentiable. So so on and so forth. So you can define any kind of differentiality by the maternal kernel. So now I'll just give you one more example of maternal 5-2 kernel, which is twice differentiable, to give you a sense of what's the difference between different kernels. Okay, so we are now using maternal 5-2 kernels, and you can make the same prediction here. Okay, so you can see here, although it's become more smooth, but it's not as smooth as RBF kernel. It's kind of set in the middle between maternal 3-2 and maternal and RBF kernel. Okay, so because we are lacking of time, so I really encourage you to play this kind of notebook yourself after this tutorial. But I have to go through. Okay, hopefully you can have some play through with these different kernel options and generate some prediction yourself, so you have a better understanding. But let me just go through this tutorial, and if you have any question, you can send an email to me. Okay, maybe I can generate a Slack so you can ask questions, like everybody can see that. Let me generate a Slack after that. Okay, so then we can have a linear kernel, right? So here I use a polynomial kernel. If you're using a polynomial kernel, if you generate any terms of polynomial, you set a polynomial degree equals 1. It's basically a linear model, right? And if we're running that, linear kernel, you can see that the prediction is basically linear. Okay, it's pretty similar to linear regression. Okay, and there's something called periodic kernel. Let's use periodic kernel to model this kind of period. If your data is kind of periodic, you might use a periodic kernel to model this kind of data. So the prediction will have some periodic in periodic in your prediction. Okay. So this is everything is quite similar. So it's kind of when you build a kernel, you just use periodic in terms of other kernels, and then you can think that the prediction have some periodicities. So even without data, you still have some periodicity in your model, which is quite useful when you model some sea level cycles. For example, if you want to model the tide, you want to model some diurnal cycle, some 17-year cycle caused by the astronomical forcing. You can use this periodic kernel. There are some papers use this periodic kernel to model some oscillation in sea level as well. Okay, so you have a lot of kernel options to reflect your prior knowledge to the process you are trying to modeling. But if something more important is that you are not limited by one kernel. You can use multiple kernels to model different sub-process of your observation. For example, if you're modeling sea level, the sea level can be changed by a lot of process, right? So sea level can change by the tide. So you can use your periodic kernel to describe the tide. Sea level can change by the climate change. You can use different kernels to describe those climate change. Sea level can be caused by some long-term process. For example, the tectonic, you can use something like linear trend to model those long-term processes. Okay, so that's what we call it, combining different kernels. Okay, so instead of using one kernel, combining different kernels really allow you to describe different process and decompose different process. So let's try to see what's going on with different kernels. Okay, so I just generate a periodic kernel look like that, and I generate a linear kernel look like that. You can kind of add them together to generate a combined kernel. Okay, so it's kind of pretty. So you can play with it later. So it's kind of, you generate one kernel, you have generate the second kernel, you add them together, you have a combined kernel, and then you use this covariant combined covariance function to draw posterior sample, to draw some samples, multivariate Gaussian samples. You see that the combined kernel is like not only model the temporal trend, but also have a periodic trend, have a periodic pattern, right? And not only you can sum them together, you can multiply them together, right? So here you can do that in PaleoSTeHM. So you can see that you kind of multiply them together. So the resulting sampling resulting in this kind of not only linear trend, but also like it's the spatial pattern is changing with the periodicity is changing with this linear trend as well. Okay, so now I will give you some practical examples. Practical examples that was mostly used to demonstrate this kind of kernel design and called kernel different kernel combining different kernels. So here is like atmospheric CO2 concentration data from Mora observatory. So here we want to model this. You can see the clear rising trend. There's a clear rising trend and a clear periodic oscillation due to the northern hemispheric summer or winter. right? We want to model that as a Gaussian process, and we want to make some prediction based on this training data. So here the blue dot maybe it doesn't seem like dot because the observation is quite high resolution in space in time, but we want to use the blue data to train the model and try to use the model to make some prediction to see how the prediction fits our testing data here. So here we are using a 5.2 maternal kernel to describe the long-term rising trend. And we are using the periodic kernel to describe the seasonality. And we are using a white noise kernel. A white noise kernel, basically you add a white noise into different data, into different data. So you are using 3 kernels. So white noise kernel, I haven't explained it. So you are adding a normally distributed, independently distributed noisy to every data point. So you're kind of adding a same level of noise to every data point. So maybe it's corresponding to unobserved noisy in your data. Okay, so this is represented as a white noise kernel. Okay, so let's do it here. So now we are defining a periodic kernel. We set some prior for the variance and set some prior for the period. It's because we know really well that the periodicity is a seasonal, is an annual cycle because it's going a summer and winter. So we set the period to have a normal distributed 1 and a variance of 0.05. This is something we can reflect our prior information in our domain knowledge in our prior distribution design. Okay, so then we have a maternal kernel. We set some prior distribution, which is kind of non-uniform, non-informative. It's just giving a range. And lastly, I just combine them. Okay, I just combine them. You see here, I can combine them as a multiplication. So I multiply them together. So you're kind of using a product kernel, a product. You see, kernel is a product operation. You input 2 kernel together, so you generate a combined kernel. So you kind of, then you can use this combined kernel in Gaussian process regression, okay, with some in train X and train Y, and what you do is exactly the same. It's exactly the same. You just try to optimize this Gaussian process. You try to optimize these hyperparameters. So one thing I haven't mentioned is that when you optimize it, you get you have a single value for these hyperparameters. This is what we call empirical Bayesian. So even though you can make some posterior conditional inference based on in a Bayesian manner, but actually you do not consider the uncertainty in your hyperparameters. This is what we call the variation empirical Bayesian method. So you have a one value for your hyperparameters. That is best fit to your data, but you actually do not consider the uncertainty, the probability distribution of your hyperparameters. This is, if you want to do that, we will cover that tomorrow. That is called fully Bayesian method. Okay, but again, empirical Bayesian method we are using here because it's computationally much cheaper. It allows you to run that much quicker compared to fully Bayesian method. Okay, so after this kind of optimization, you can see how does each kind of parameter optimize here, and then we can use this optimized hyperparameters to do some predictions. Okay, so you see here, because we have some periodicity. So even though we don't have any observation data here, you see the purple dot here. It's like we do not include any data here. I just compare our prediction with data. So even we don't have data to inform us it should go up and down because we are using a periodic kernel. It should go it go up and down as a prediction. And because we infer the length scale, so the length scale tells us how much further away from the observation this kind of inference uncertainty will increase. So because so here, when we move further away from our data, the inference result will converge to prior, which is mean, which is 0, because we are using the zero means as our prior. I hope that makes sense. Okay, so we have like several seconds. So let me just explain a little bit more about what I mean by empirical base and variational base. Empirical base and fully Bayesian. So I think you can find that in here, analysis choices. So if you have any question, just feel free to. So here is like, okay, so here is what we did before, right? We have one value for length scale and one value for the variance parameter, right? So then you make any Bayesian inference based on these two hyperparameters, right? But if you do some fully Bayesian, right, you can do some MCMC, right? You do some MCMC, you can sample the posterior distribution of your length scale and your variance of any of your hyperparameters, right? So you can have a posterior distribution of your hyperparameters, so you can have a more rigorous uncertainty estimate in the final result. So if you compare them, but also you can use variational base, right? You cannot, if you can use MCMC, you can use variational base. So to use a variational base, you can check out this tutorial later. Okay, so variational base is like kind of approximate posterior distribution based on some known parametric form, right? As I said before. So if you compare them together, you can see that if we run an empirical base, we basically have one hyperparameter estimate, right? But if we use fully Bayesian or variational base, we can have a posterior distribution of our hyperparameter, and our estimates for our inference is more robust because it's considering the uncertainty in our hyperparameter as well. Here is an example like how here like you cannot see too much difference, but actually there are multiple papers showing out that if you are using empirical base, your kind of inferred uncertainties can be underestimated a little bit. But if you use empirical base, it's much more computationally cheaper. So something I haven't mentioned about Gaussian process is that you do need to do some matrix inversion. So matrix inversion, because if we have more and more data, this kind of square distance matrix is become larger and larger. And then the computational power you need for inverse this matrix is scale cubically with the amount of your data. So Gaussian process can be really, really slow if you have a lot of data, let's say 10,000 data. So now we try to run like 5,000 data. It's kind of optimization. Empirical based optimization may take you 30 minutes, something like that. So in this case, you cannot run fully Bayesian because it takes you, you can run, but it takes you maybe several days to run that. But maybe after several days, you find out the result is not that promising. So it's kind of annoying. So sometimes the rule of thumb is you start with empirical base or variational base, so you have a better understand before you went to fully Bayesian method. So this different but this kind of different analysis choices have no relationships of what kind of process level model, what kind of data level model you are using, because no matter what kind of data level model, what kind of process level you are using, you can pair them with any type of optimization or analysis choices. Okay, I hope this makes sense to you. So that's